Handling missing and dirty bank data in Python. In real-world banking, data issues like missing or incorrect values are common. Identifying and fixing dirty data is vital for accurate reporting and risk assessment. This lesson covers how to find, clean, and handle missing or dirty data using Pandas. You will practice hands-on techniques for cleaning up messy transaction and customer data. By the end, you will be able to prepare banking datasets for analysis or machine learning. Running the cell now. We import Pandas to work with data frames and tabular data. We import NumPy for advanced numerical and array operations. We import Python's warnings system. We ignore warnings to keep our notebook output clean for demonstration. Running the cell now. Setting up our working environment is the first step in cleaning data. Core concepts: understanding banking data problems. Banking data includes transactions, customer details, and account records. Data can become dirty through missing fields, typographical mistakes, or inconsistent entries. Beginners often forget to check for missing data, assume data is always clean, or use the wrong fill values. Running the cell now. Now we will create a sample banking transactions dataset for practice. We start creating a synthetic data frame for banking transactions. We set C to 42 for reproducibility so results stay the same every run. We specify 1,000 transactions. We specify 200 unique customers. We create a transactions data frame. We use unique incremental numbers for transaction IDs. We randomly assign each transaction to a customer. We generate realistic random amounts using a normal distribution. We randomly choose debit or credit for each transaction type. We assign different transaction channels randomly. We generate hourly transaction timestamps. We print the shape of the data frame to see dimensions. We display the first 3 rows as a preview. Running the cell now. This output shows a synthetic banking transactions dataset with 1,000 rows and 6 columns, representing key features like transaction ID, customer ID, amount, type, channel, and date. Notice the variety in transaction types and channels, reflecting real-world complexity, and the sequential hourly dates, which will be important when identifying data issues. This setup helps beginners grasp the structure and potential messiness in banking data before cleaning or analysis. Try printing df.tail 3 to see the last 3 records in the data frame. Let us also create a synthetic customers table to use for validation and cleaning practice. We prepare a list of customer IDs. We create a data frame for customer information. We assign customer IDs to the table. We label the first 150 customers as retail and the rest as business segment. We assign the first 100 customers to metro region and the rest to regional. We print the dimensions of the customer's data frame. We preview the first 3 customer records. Running the cell now. This output shows our synthetic customers data frame has 200 rows and 3 columns, representing customer IDs, segments, and regions. The first 3 rows confirm the consistent structure and clean data with no missing values, aligning with our lesson focus on checking basic data integrity before proceeding with analysis. Noticing the balanced segments and regions helps ensure our dataset mimics realistic banking customer distributions. What other customer columns would be typical in a real bank? Think and list too. Beginner step, let us check our transactions for any missing data. We call isNull on the whole data frame to identify missing values. We sum missing values for each column to get a count. We print out how many missing entries there are in every column. Running the cell now. This output shows the count of missing values for each column in the banking transactions data frame, with all values at 0 indicating no missing data. It's important to note this step verifies data completeness before analysis, reinforcing the lesson's point that beginners must always check for missing entries rather than assuming data is clean. This quick check helps prevent errors later when working with transaction or customer records. Try this on the customer's data frame to compare missing values there. Now we will add some missing and dirty values to simulate real bank problems. We set amount to missing in row 4 for demonstration. We set customer_ID to missing in row 6. We add a typo to the dechanneled column for row 11 by using lowercase characters. We print the first 12 rows to observe the intentional dirty data. Running the cell now. This output shows the banking transactions table with deliberate data issues to practice cleaning. Row 4 has a missing amount, none. Row 6 a missing customer_ID, none. And row 11 a typo in the channel, online. Notice these inconsistencies disrupt data integrity, highlighting why beginners must identify and handle missing or incorrect entries before analysis. This sets the stage for learning strategies to detect and correct common banking data problems. Can you spot the dirty or missing values in the printed output? Let us identify how much dirty data we have in each affected column. We count and print rows where amount is missing. We count and print rows where customer_ID is missing. We count and print rows where channel is typed as online in various cases. Running the cell now. This output reveals key data quality issues in the banking dataset. There is one missing value each in the amounts and customer_IDs columns, which are critical for analysis. Notably, the channeled column has 237 entries that may contain typos or inconsistent capitalization, indicating a need for careful cleaning. This aligns with the lesson's intent to emphasize the importance of identifying missing or inconsistent data early to avoid errors in downstream processing. What other dirty value scenarios can you think of in banking transaction data? In business, missing amounts may be filled with the column average as a quick fix. We calculate the mean transaction amount. We fill missing amounts with this calculated mean. We print the top 6 records to verify missing values are filled. Running the cell now. Here we see the first 6 rows of the banking transactions data after filling missing amounts with the average transaction value, about 180. This ensures no numeric gaps in the amount, which is crucial for accurate financial analysis, while other columns like customer_ID still show missing data. The key takeaway is that handling missing numeric values prevents errors downstream, but remember to address non-numeric gaps separately. Try changing the fill value to df, amount.median, and see what happens. Let us fill missing customer IDs with an unknown placeholder instead. We fill any missing customer_ID with the word unknown. We print the specific row 6 to check if the fill worked. Running the cell now. Here we see that the missing value in the customer_ID column has been replaced with the placeholder unknown for row 5. This step is crucial because it prevents errors during analysis by ensuring there are no empty fields. It also highlights the importance of handling missing data correctly rather than leaving it blank or using inappropriate defaults. For what field should you avoid using placeholders like unknown in banking? Let us fix inconsistent capitalization in the transaction channel column. We use street title to standardize channel names like online and online as online. We print all unique channel values to confirm they are consistent. Running the cell now. The output shows the unique values in the channeled column after standardizing the text-to-title case, correcting inconsistent capitalization like BTM or BTM. Notice how this step helps ensure that similar channels are grouped uniformly, which is crucial for accurate analysis and reporting in banking data. This highlights the importance of cleaning text entries to avoid errors from case mismatches in categorical data. Try using street upper or street lower and compare the differences in cleaning. Sometimes it is better to remove records missing mandatory fields like customer ID. We store the number of rows before dropping. We remove any rows where customer_ID is unknown. We store the number of remaining rows. We print out how many rows we had before and after cleaning. Running the cell now. This output shows the effect of removing rows where the customer_ID is missing or marked as unknown. Notice only one row was dropped, indicating very few missing critical identifiers in this dataset. This step is important to ensure analysis uses only valid, identifiable customer data, emphasizing the lesson on cleaning and validating banking records. Test what happens if you drop rows with missing amount instead. Now let us handle outliers, which can be a sign of input error or fraud. We locate all transactions whose amounts are above 1,000. We cap those outlier amounts to 1,000 for business safety. We print the rows where we replaced the values to check results. Running the cell now. This output shows an empty data frame, meaning there were no transaction amounts exceeding 1,000 to replace. This result highlights the importance of checking for outliers before applying domain rules. If no outliers exist, the data remains unchanged. It also reinforces careful data inspection in banking datasets to avoid unnecessary or incorrect adjustments. Practice: replace all negative amounts with 0 instead. Duplicate transactions can be a common error. Let us remove them. We find duplicates based on customer ID, amount, and date. We keep only non-duplicate rows. We print the new row count after deduplication. Running the cell now. This output shows that after removing obvious duplicate transactions, those with the same customer ID, amount, and date, the dataset now contains 999 rows. Notice how the code targets key columns likely to define duplicates in banking data, improving data quality by reducing redundancy. This step is crucial because duplicates can skew analyses, and beginners often overlook removing them before further processing. What other columns might you use to spot duplicate transactions? Let us enrich our transaction data by merging with customer segments and regions. We join transaction data with customer profiles on customer_ID using a left join. We print the first 3 merged records for inspection. Running the cell now. This output shows the first 3 rows after merging transaction data with customer profiles using a left join on customer_ID, enriching transactions with customer segment and region details. Notice the expanded columns and complete customer info next to each transaction, which is crucial for identifying patterns like spending behavior by segment. This step highlights the importance of merging to combine datasets for deeper banking data analysis while being mindful of potential missing merges. Try merging on different keys for different banking scenarios. After merging, let us find transactions that still lack real customer details. We filter for merged records where segment is missing. We print a heading for context. We print the actual transactions with no customer match. Running the cell now. This output shows that there are no transactions lacking matching customer information, as indicated by the empty data frame. It confirms that the merge between transaction and customer data was successful without missing segment values, highlighting the importance of verifying data completeness before analysis. This check helps prevent errors from missing customer details in banking data workflows. How would you resolve these unknowns to avoid downstream errors? When categories are missing, it is common to fill with the most frequent value. We determine the most common transaction channel in merged data. We fill missing channel values with this most frequent entry. We print the imputed value used for filling. Running the cell now. This output shows that the missing values in the channel column were filled using the most common transaction channel, which is the ATM. This approach ensures consistency by replacing blanks with a realistic category, highlighting the lesson's point about carefully handling missing data instead of ignoring it or using arbitrary values. Noticing the chosen mode helps reinforce why filling with a common but contextually relevant value matters in banking data. As practice, fill missing segment values with the most common segment. Always use error handling when making risky changes to real bank data. We start a try block for safe error handling. We attempt to convert the amount column to floats. On success, we print a confirmation message. If an error occurs during conversion, we print what went wrong. If an exception is raised, it is displayed clearly by the print statement. Running the cell now. This output shows that the code successfully converted the amount column to a float data type without errors, indicating the data was clean enough for this operation. In the lesson context, it highlights the importance of using try-except to catch potential issues during risky data cleaning steps, such as type conversions in banking transactions. This ensures your workflow handles dirty or unexpected data gracefully instead of crashing. Try purposely passing a string to amount to see error handling in action. Let us write a reusable function to clean invalid records safely. We define a function drop_invalid for a data frame and column. We count and display how many invalid values are found in that column. The message shows which column is being cleaned and how many rows are dropped. The function returns all rows where the value is not missing. We use the function to drop records with missing customer IDs from merged data. Running the cell now. This output tells us that there were no missing values in the customer_ID column when we checked the merged dataset. This confirms that the customer IDs are complete, which is crucial for linking transactions to customers reliably. The code's intent here is to catch and remove any invalid or missing IDs to maintain clean, trustworthy data for analysis. Adapt drop_invalid to log dropped row indices for an audit trail. In real banking, you will want all cleaning logic in one repeatable function or pipeline. We define a function to clean transaction data step by step. We make a copy of the input data frame for safety. We fill missing amounts with the median value. We fill missing customer IDs with unknown. We standardize channel text to title case. We drop any records with unknown as customer_ID. The function returns the clean data frame. We run our full clean and print a preview. Running the cell now. This output shows the first 3 clean transactions after applying a pipeline that fills missing amounts with the median, replaces missing customer IDs with unknown, capitalizes the channel names, and removes unknown customers. Notice the consistent channel formatting, e.g., ATM instead of ATM, and no missing customer IDs, which ensures cleaner, more reliable data for analysis. This reinforces the lesson's core concept of handling missing and inconsistent data systematically in banking datasets. Customize clean_transactions to add duplicate removal or additional rules. End-to-end example, clean dirty bank data and report. Now let us load, dirty, clean and summarize transaction data in one workflow. You will see how the pieces come together with real business value. The final result will be a quick summary report ready for decision-making. Running the cell now. Let us go from dirty input through cleaning to business summary in one shot. We copy the transactions table to DF2 to avoid breaking the original. We insert a nonsensical negative amount in one transaction. We create a missing customer_ID to test cleaning. We add a mixed case typo in the channel column. We use our cleaning function to standardize and fix all issues. We create a channel by amount summary suitable for reporting. We print this report for use by business teams. Running the cell now. This output shows the summary of transaction counts and average amounts grouped by channel after cleaning the dirty data. Notice how the counts are roughly similar across channels, reflecting a balanced dataset, while the mean amounts vary slightly, which could influence channel-specific business decisions. This demonstrates how cleaning and aggregation together provide a clear, actionable report from messy raw data. Practice, try changing the group B to transaction_type for a different business insight. If you are learning something new, subscribe to Python Banking for more tutorials on YouTube. Recap and next steps. You learn techniques to detect and clean missing or dirty data. Practice on realistic bank transaction tables. Explore outlier handling, merging, and safe error handling. Build your own cleaning pipelines for any messy banking dataset. Visit our YouTube channel for deeper dives and more banking data science workflows. Running the cell now.